There are some properties satisfied by the relations. One is reflexivity. Let R be a relation in a set A. Then R is reflexive if for every x element of A, xx is element of R. There is a relation in a set A is reflexive. Every element of A is related to itself. You can also write the same thing as x r x for every x element of A. If this condition is satisfied, such a relation is called a reflexive relation. Some relations are reflexive, some are not. Some relations are reflexive, some are not. For example, among real numbers, the relation less than or equal to is reflexive because for every real number x is less than or equal to x. Whereas if you take among real numbers itself, you take the relation less than. X is less than x is never true. So this relation is not reflexive. Less than is not reflexive. Among subsets of a set, subset of is a reflexive relation. Whereas proper subset of is not a reflexive relation. A is not a is a subset of A, but A is not a proper subset of A. So proper subset of is not a reflexive relation. So there are relations which are reflexive, there are relations which are not reflexive. You can see that a relation R is reflexive if and only if delta is a subset of delta is the collection of all ordered pairs xx, and relation is reflexive if and only if delta is continuous. Delta a different. So this is the definition of a reflexive relation. Now another definition is a relation R in a set A is symmetric if for every xy element of A, xy element of R implies yx element of R. Or you can also write it as for every xy element of A, x related to y implies y related to x. Such relations are called symmetric relations. Some relations are symmetric and some are not symmetric. Among human beings, x loves y is not symmetric. If x loves y does not imply that y loves x. Sibling of x is a sibling of y is a symmetric relation. Equal to is a symmetric relation. Whenever x is equal to y, y is also equal to x. So that is a symmetric relation. But subset of is not a symmetric relation. A is a subset of B does not mean that B is a subset of A. Superset of A is also not symmetric. Among lines in a plane, Parallel is a symmetric relation. L1, a line L1 is parallel to line L2 implies that line L2 is parallel to L1 also. There is a symmetric relation. So there are relations which are symmetric and there are relations which are not symmetric. Now, if a relation is symmetric, it is clear that R is the same as R inverse. If a relation R in a set A is symmetric, then R is the same as R inverse. Why? xy is an element of R. If and only if yx is an element of R. And R inverse is nothing but the collection of all xy where yx belongs to R. So these two, they are one and the same. Oh, and the converse is also true. If this relation is satisfied, then R is symmetric also. So we can say that R is symmetric if and only if R is equal to R inverse. Another property is transitivity. A relation R is transitive if for every x, y, z in A, x, y in R and y, z in R implies x, z in R. Or for every x, y, z in A, x related to y and y related to z implies x related to z. Such relations are called transitive relations. For example, equality is a transitive relation. A equal to B, B equal to C implies A is equal to C. Subset of is a transitive relation. A is a among subsets of a particular set. Subset of is a transitive relation because A is a subset of B and B is a subset of C implies A is a subset of C. Less than or equal to is a transitive relation. A less than or equal to B and B is less than or equal to C implies A is less than or equal to C among, say, real numbers. Among integers, divides is a transitive relation because A divides B and B divides C implies A divides C. So we are having a lot of relations which are transitive, but there are many relations which are not transitive also. For example, x is a friend of y among human beings is not a transitive relation. X is a friend of y, y is a friend of z does not imply that x is a friend of z. Friend of a friend need not be a friend. X loves y, y loves z does not imply that x loves z. Several, not transitive. There are several examples. Not equal to x not equal to y, y not equal to z does not imply that x is not equal to z. It can happen that x and z are one and the same where x and y are different and y and z are different. So not equal to is not a transitive relation, whereas equality is a transitive relation. Among integers, we can say that two integers are neighbors if the modulus of the difference is equal to 1. That is, x and two integers x and y are neighbors if x minus y is equal to 1 or y minus x is equal to 1. 1 and 2 are neighbors, 2 and 3 are neighbors, but not 1 and 3 are not neighbors. So that relation is not transitive. So we have relations which are transitive, and we are also having which are not transitive. Among the collection of all lines in a plane, L1 parallel to L2 is a transitive relation. L1 parallel to L2 and L2 parallel to L3 implies that L1 and L3 are, L1 is parallel to L3. So that relation is transitive. So we are having three properties of relations: reflexivity, symmetry, and transitivity. A relation satisfies two of these properties does not imply that it satisfies the third property. For example, if a relation is reflexive and symmetric, that need not be transitive. If a relation is symmetric and transitive, that need not be reflexive. If a relation is reflexive and transitive, that need not be symmetric. Homework, find such examples. Homework, find examples of relations satisfying any two of these three properties, but not the third one. Among lines in a plane, the relation two lines are distinct parallel lines is a relation which is symmetric and transitive but not reflexive. Distinct parallel lines. Less than or equal to is reflexive as well as transitive but not symmetric. Find several such examples. But in mathematics we are interested in some relations which satisfies all these properties, these three properties. Such relations are called equivalence relations. It is tilde is an equivalence if tilde is a relation in a set A, then tilde is an equivalence relation if it is reflexive, symmetric, and transitive. A reflexive, symmetric, and transitive relation is called an equivalence relation. Okay, I can write R itself here. Just change the notation. And normally it's a practice to use the symbol tilde for equivalence relations. I think this symbol comes from Spanish language. Spanish, just like other European languages, use the Roman letters with some modifications, and this is one of the modifier used. Tilde. It is available in the keyboard, and in mathematics we use this symbol very frequently, and many times it is used to represent equivalence relations. There is one important example of equivalence relation among integers. Take the set of all integers. This is not just z. This is z with an additional line like this. This symbol is reserved for the set of all integers. Second, common practice to denote the set of all integers by this symbol. Why this symbol z? It looks a bit strange if we are not familiar with German. In the German language, there is a word Zahlen starting with Z, used for integers. Zahlen means integer. So, in the German textbooks, Z was used to represent the set of all integers, naturally. And when some of the German textbooks were translated to English, they use the same notation. There is a case with several of the notation, because even though as the former subjects of the Queen, we are Queen and the King, British Queen and Kings, we are having a exaggerated view about the importance of English. But among the European languages, English was not considered as great as equivalent to, say, German or French or even Russian. English was not considered that. Even some of the best contributions of Englishmen are not written in English, like the great work of Isaac Newton, etc. So this notation comes from German, Zahlen. So you take a set of all integers. Now you take a positive integer n. Suppose n is a positive integer. Then we have this x congruent to y mod n if n divides x minus y. This relation is very important in number theory. That is, an integer x is congruent to another integer y modulo n if n divides x minus y. N is a fixed positive integer. Now this relation is reflexive because x is congruent to x mod n. Why? Because n divides x minus x. X minus x is 0. N divides 0. And x congruent to y mod n, this implies that y congruent to x mod n. Why? When n divides x minus y, n also divides y minus x. And this relation, so this relation is reflexive, and also this relation is symmetric. It is also transitive. X congruent to y mod n and y congruent to z mod n implies x congruent to z mod n. Why? Because n divides x minus y, n divides y minus z, therefore n divides their sum. The sum of x minus y and y minus z is x minus z. So n divides x minus z. Therefore, x is congruent to z mod n. Now we can have a break for 15 minutes. By the time we can expect that this relation is also transitive. That is, x is congruent to y mod n and y is congruent to z mod n implies x is congruent to z mod n. Why? X is congruent to y mod n means n divides x minus y. Y is congruent to z mod n means n divides y minus z. Therefore, n divides x minus y plus y minus z, that is x minus z. So, n divides x minus z, which means x is congruent to z mod n. So, this relation is reflexive, symmetric and transitive. So, this is an equivalence relation. This is a very important equivalence relation in number theory. Now, you take the set of all lines in a plane. Two lines are related if they are parallel. That is reflexive. Every line is parallel to itself and it is symmetric. X is parallel to y, implies y is parallel to x. X is parallel to y and y is parallel to z implies x is parallel to z. So, this relation is reflexive, symmetric and transitive. So, we are having a lot of relations which are reflexive, symmetric and transitive. They are called equivalence relations. Now, suppose x is a set and tilde is an equivalence relation on x. You take one particular element, say a of x. Then you can take the set of all elements which are equivalent to a. That is, you take the set of all x element of x such that x is equivalent to a. Usually that is denoted by some symbol like this. Some people use that is the set of all elements of the set which are equivalent to this particular element. So, for every element we can define such a set. This is called the equivalence class of So, for every element we can define the equivalence class of that element. Clearly, A is an element of the equivalence class of A because A is equivalent to A by reflexivity. Also, you can see that if you take two elements A and B, their equivalence classes are either equal or disjoint. For AB, the equivalence class of A and equivalence class of B are either equal or disjoint. Disjoint means their intersection is empty. If intersection of two sets A and B is empty, we say that A and B are disjoint. So, for elements A and B, one possibility is that equivalence class of A and equivalence class of B are one the same, or they are disjoint. This can be proved easily. Suppose that equivalence class of B is not the same as equivalence class of A. Then we have to prove that equivalence class of A and equivalence class of B are disjoint. Suppose not. Suppose that there is some C in equivalence class of A intersection equivalence class of B. That is, C is an element of equivalence class of A, and also we have that C is an element of equivalence class of B, in which case C is related to A and C is related to B, and C is related to A implies A is related to C. A is related to C and C is related to B implies by transitivity A is related to B. Now if A is related to B, what happens? If A is related to B, then every element related to A will be related to B also by transitivity. In which case we have that the equivalence class of A will be contained in the equivalence class of B. Since A is related to B, B is also related to A by symmetry, which implies that equivalence class of B will be contained in equivalence class of A. Consequently, equivalence class of A will be the same as the equivalence class of B, which is not the case. Our assumption is that equivalence class of B and A are different. So we'll get that if the equivalence class of A and B are different, then they are disjoint. So for any two elements A and B, either their equivalence classes are equal or they are disjoint. So this is an important property of equivalence classes. Now we can take the collection of all equivalence classes. Say you take the collection of all equivalence classes. Sometimes this is denoted by the symbol x over tilde. That is the equivalence classes of elements of X with respect to the equivalence relation tilde. Sometimes this is called the quotient. This set is called the quotient of the set X. Now, these equivalence classes, these are all actually subsets of, is a collection of subsets of X. This collection of subsets of X is having a property, having two properties. One property is that the union of all these sets I should write for every X element of X, X is an element of some equivalence class. Every element belongs to some equivalence class, because the equivalence class of that element. If X is an element of X, X is having an equivalence class, and X is an element of the equivalence class of X. So every element belongs to some equivalence class. And also we have that if you take two equivalence classes which are distinct, then they are disjoint. Such a collection of subsets of a set is called a partition. So a partition is actually a collection of subsets of a set with these two properties, that every element of the master set is in one of these sets, and any two sets are either equal or disjoint. Such a collection of subsets of a set is called a partition. And the point is that the collection of all equivalence classes with respect to an equivalence relation is a partition. For example, we were discussing the set of all integers and the relation congruent modulo a positive integer. For example, take n is equal to 2. N is equal to 2. So, what is meant by saying that two integers are congruent modulo 2? That means 2 divides x minus 1. When do we get that 2 divides the difference of two integers, or that the difference is is an even number? For two integers, when is the difference an even number? You take two even numbers, their difference is an even number. If you take two odd numbers, their difference is also an even number. And if you take an odd number and even number, the difference is not even, it is odd. If you take the difference of an odd number and an even number, the difference is odd. So, the difference is even if and only if both of them are even or both of them are odd. So, that means two integers are congruent modulo 2 if and only if both of them are even or both of them are odd, or they have the same parity. So 2 and 3 are not congruent modulo 2, whereas 3 and 5 are congruent, but 3 and 6 are not congruent. 1 and 2 are not congruent. If that is the case, then how many equivalence classes will be there? The equivalence class of 0 will contain all the even integers, and the equivalence class of 1 will contain all the odd integers, and there will be only two equivalence classes. These two equivalence classes, odd integers and even integers, form a partition of the set of all integers. This is the situation when n is equal to 2. Now, when n is equal to 3, you may get another partition as the equivalence classes. When n is equal to 4, you will get another partition as. And this kind of the equivalence classes with respect to this congruence relation is they are having a special name. They are called residue classes. That is, you take the set of all integers and use this congruent modulo n as the equivalence relation, and the corresponding equivalence classes are also called residue classes. They are important in number theory and algebra. We can also ask another question. Can we, from an equivalence relation, we had obtained a partition. Can you do it the other way? Suppose you start with a partition. Suppose that script P is a partition of a set X. That means P is a collection of subsets of X with the property that every element of X is in some set in script P, and given any two sets in script P, they are either equal or disjoint. So that is what we mean by saying that P is a partition of X. Now suppose that we are having such a partition. Now we define a relation like this. We define for xy elements of X, we define X related to Y if if there exists a set capital P, an element of script P, such that X is an element of P and Y is also an element of P. If there is a set in script P containing both x and y, we say that x and y are related, otherwise not related. This relation is reflexive. Why? Because x and x always belongs to the same set. If x and y belongs to the same set, y and x belongs to the same set. If x and y belongs to the same set and y and z belongs to the same set, then x and z belongs to the same set. So this relation is reflexive, transitive, and also symmetric. So this will be an equivalence relation. So once you start with an equivalence relation, you can arrive at a partition, and if you start with a partition, you can define an equivalence relation also. So such a correspondence, such a one-one correspondence between the set of all equivalence relations on a set and the set of all partitions of a set is that. We'll discuss that later. The concept of equivalence relations and the corresponding partition, this is very important in mathematics and various applications of mathematics. Sometimes we will be considering a particular set of objects. Of course, set theoretic point of view, we are only considering the distinct objects. But in a particular point of view, it can happen that even distinct points are to be considered similar. Why two objects are different? Two objects are different because there is some property possessed by one and not by the other. But in order to distinguish between all the objects in a very large collection, a set, we may need a lot of properties. But sometimes we may not be, we may be having only a small number of properties. For example, when we consider a database of objects, and we will be interested only in a small number of properties because we want to make our database finite and small so that it is manageable. Then it can happen that two items of the database are different, but both of them are having the same properties with respect to this particular database, because we are only considering a small number of properties. In such a situation, naturally there will come an equivalence relation. Similar objects are, that relation is reflexive, symmetric, and transitive, and that will divide your set into equivalence classes. This is a topic we'll discuss more if you when we discuss rough set theory. This point is very crucial in the discussion of rough set theory. We'll discuss that later. Even in mathematics, such things happen very frequently. For example, what is a quotient? What is a rational number? Rational number is actually a quotient of two integers, a and b, of the form a by b, where b is not equal to 0. Now you consider the quotients like this: 1 by 2 and 2 by 4. 1 by 2 and 2 by 4 are not different numbers, they are one and the same. So these two numbers are considered one and the same, even though This is the quotient of 1 and 2, this is the quotient of 2 and 4. But they are to be considered identical. This is how we develop the collection of all rational numbers from integers. A rational number is actually a quotient of two integers, the second one not equal to 0. So you can consider the collection of all ordered pairs of integers with the second one not equal to 0. Second coordinate not equal to 0. But there will be a large collection, and among them we will define an equivalence relation. For example, we want the ordered pair 1, 2 and ordered pair 2, 4 to be identical. So we will define an equivalence relation between such things. That is, ordered pair AB and ordered pair CD are, if what will be the condition? A plus C is equal to B plus D, something like that. Our idea is that A minus B is equal to C minus D, or in other words, A plus C is equal to B plus D. So this will be an equivalence relation among the ordered pairs of integers, and the equivalence classes are to be defined as rational numbers. The same trick works to construct integers out of non-negative integers, because each integer can be considered as a difference of two non-negative integers. But 2 minus 1 and 3 minus 2 are one and the same. So you take all non-negative integers and you take all ordered pairs of non-negative integers, then you put a equivalence relation among those ordered pairs, and what will be the idea? That is, AB is related in that case to CD. If the idea is that A minus B is the same as C minus D, or here the idea is that A by B is the same as C by D. So that is to be written as AD is equal to BC. Here there is A plus C is equal to B plus C. This was a mistake. Should have been correct. Here from in the construction of rational numbers out of integers, we have to use this equivalence relation, that the ordered pair AB and CD are related if AD is equal to BC. Whereas when we construct integers out of non-negative integers, you have to use this equivalence relation. Such constructions are very frequent in mathematics. They are called quotients. Quotient of a suppose you have taken one abstract space, and we will consider the equivalence classes of elements of that set as, and we will put a structure on that set also. We will get quotient spaces. This is very important in mathematics.